All right, so the question then becomes, and let's not forget though that even though these are different than what you would expect, they still occurred when we were sampling from a population that exactly matches what was claimed, this null hypothesis, that the color distributions match. So these are just not bad samples, they're just unlucky samples, right? Where we happen to get maybe a bunch of greens and not very many yellows or something like that. But that just happens when we do chance processes, okay? So what's our p-value? Well, our test statistic was 14.07, so that's like right there. There were only 2 simulations that got a chi-squared test statistic bigger than ours. So there's only 2 out of 100 that were as extreme or more extreme than ours. So that's a p-value of 0.02. Therefore, we would reject the null. We would reject the hull. We would say, you know what? They're not the same. They don't match the distribution that's claimed. At least 2 of the colors is not equal to the claimed value. Okay? So that's how we run. That's exactly how we run a hypothesis test. This is a chi-squared. We're going to learn that it's a goodness of fit test. Okay. Now we are not going to use this simulation. Instead, we're going to come up with a nice, smooth theoretical model to model this chi-squared distribution. Okay. This, just like we came up with a theoretical normal model and a theoretical t-distribution. All right. All right. So Section 11.1 is a chi-squared goodness of fit test, which is exactly what we ran back here with the simulation. So first of all, the chi-squared test statistic, here it is as it is written in the book. Observed minus, okay, I said expected minus observed. It doesn't matter when you square it. If you get you're going to get an opposite sign on your difference, but when you square it, it doesn't matter. So I guess I should start doing OBS minus expected. And you sum it for all possible values of the categorical variable, just like we did before. Now we need to analyze this chi-squared distribution. So a chi-squared, there's a family of density curves. Remember, density curves have an area of 1 underneath it. And it's a family, so it's got a bunch of, for every different degrees of freedom, there's a different curve. So here's the curve with 1 degree of freedom, with 4 degrees of freedom, and with 8 degrees of freedom. I don't know, in class I plotted it and kind of showed it to you with a bunch of with a slider. Maybe I'll pause the video and show that to you real quick. All right, so we can plot this on our calculator. The function you plot on the calculator is actually the chi-squared PDF. Now, if you remember, the PDF is the one you don't ever use for the Z's and the T's, the normal and the student T. You never use PDFs because we never plot these things, right? They're all, now, and the same with the chi-squared. We're only using this to plot it, and I'm not going to ask you to plot it. You're going to have to use the CDF and the inverse chi-squared in order to answer questions in class. But just to illustrate what the curve looks like, here it is with 1 degree of freedom, 2. God, I need to go higher up. Wait, 4? I don't want to go higher up because, okay, you're not really seeing the top. The top is there. So at 2, it's got a peak up there. At 0. At 3, it's got a peak kind of at 1. And it's basically just this family of curves. As you can see, as the degrees of freedom gets bigger, it kind of slides to the right, but it's always skewed to the left. Now, if you look at 7 degrees of freedom, let's see if we can find the peak. Menu, analyze, maximum, click, click. The maximum happens at 7. So the mode or the peak of the distribution is always 2 less than the degrees of freedom. Okay, 6 at 8, so on and so forth. It goes off, you got to redo it, but okay. All right. And then as it moves, so it's always skewed to the right. Now, as the degrees of freedom get larger, it becomes a little bit less skewed, but it still is going to be skewed to the right always. Okay. So that's the family of the chi-squared distribution. Notice it never is negative; it's always positive, and we'll talk about that here. Some properties: the mean of the distribution is equal to the degrees of freedom. So if the degrees of freedom is 4, then that's going to be the mean of the distribution. The mode, or peak, is going to be 2 less. We kind of saw that on that other graph. It's always skewed to the right, and it only exists for positive values. A little star by that, you really should put that to kind of memory. All right, so we aren't going to graph these things in our class. However, I would expect you guys to use your menu, statistics, distributions. I do expect, just like you use the normal CDF and inverse normal and T-CDF and all that, I do expect you to use the chi-squared CDF and the inverse chi-squared appropriately. So if I got 5 degrees of freedom, so the mean is at 5, the peak is going to be at 3, skewed to the right. Find the probability that your chi-squared is greater than or equal to 12. So if 12 is here, it's the area to the right of 12. So we can still draw this picture. We can still label the cutoffs. And we can still find the probability that your chi-squared is bigger than 12. That's going to be from 12 to infinity. That's going to be the chi-squared CDF, lower bound 12, upper bound infinity, degrees of freedom 5. 0.0348. 0.348. Okay. Given this curve, find the value that has 15% to the right. If it's got 15% to the right, it's got 85 to the left. Now, I told you the degrees of freedom here. Now, you should have been able to get it from the drawing. If you would have gone down 2, 4, this is at 6. If the peak is at 6, then the degrees of freedom is 8. But they gave it to us. We didn't have to do that. So I want the area that has 85% to the left under 8 degrees of freedom. That's going to be the inverse chi-squared function. 0.85. Was it 8 degrees of freedom? 12.03. 12.03. Looks about right. Chi-squared is approximately 12.03. All right. So that is a chi-squared curve. All right. So we'll finish up this video by just talking about the chi-squared goodness of fit. We've kind of got everything laid down. We ran it earlier. Let's just formalize it and use our theoretical model. If the conditions are met, this is going to be our null and alternate. This is how the book words it. I prefer mine. The true distribution of the population matches the claim distribution. The true distribution of a categorical variable in the population of interest matches the claim distribution. Actually, I should have put true distribution of a categorical variable. I should have put that in there. But I like saying it matches a claim distribution. Or the true distribution of a categorical variable in the population does not match. So the null is it matches, the alternate is that it doesn't. We're always dealing with counts. Chi-squareds are always one-tailed tests. Oh, another thing I should mention. The degrees of freedom when you're running these tests is k minus 1, where k is the number of categories. So in this previous example, we had the previous activity, we had 6 colors. So there were 6 responses to that categorical variable. So if you take 6 minus 1, this would be a degrees of freedom of 5. So this is actually a 5 degrees of freedom. In fact, the peak should be at 3, right? We now know, and that looks about right. Peak is about at 3. This is 5 degrees of freedom. We're not going to construct confidence intervals in this class. That would be BAPS, Beyond AP Statistics. However, if you do confidence intervals for standard deviation, you would use chi-squared. Conditions, random. Got to have a good random sample. 10% condition, as long as you're not doing an experiment, check it. And large counts. This time, though, instead of saying n times p is greater than or equal to 10, all of our expected counts need to be at least 5. So it's a different check, kind of the same. We're still checking the counts, but expected counts bigger than 5. The observed counts can be anything. Don't look at the observed counts when you're doing that check. Okay? This is not a normality check. What is it? It's a check to see if your chi-squared test statistic really has a nice, smooth chi-squared distribution. It's a check to see if your statistic in your example, in your situation, matches this theoretical smooth density curve. So yeah, that's it. All right, so we're going to look at an example and then we'll be done.